Question for you. If a fighter jet doesn't need a pilot, why does it still need a bespoke supply chain? Fury's answer is, it doesn't. In this video, we break down the engineering decisions that let Anduril spread production across hundreds of US suppliers. Commercial engine, simplified landing gear, software-led testing, contrasted with the specialized choke points that slow conventional fighters. The payoff. A concrete, step-by-step view of how industrial design, not exotic materials, drives cost down and throughput up. Before we move on, please take a moment to subscribe to the channel and like the video. A fighter that drops the pilot and the boutique parts list changes throughput because it removes two chronic choke points, flight-rated subsystems that only a handful of vendors can touch, and certification paths that freeze hardware while paperwork catches up. Traditional fighters run on narrow lanes. You get specialized alloys with controlled chemistries, single-source landing gear built on proprietary forgings, and engines restricted to defense channels with scarce spares. Each element is qualified to a unique drawing stack, so a delay at one supplier halts final assembly. And even simple design updates ripple through months of requalification. It was therefore normal to see long lead items dictating schedule rather than airframe readiness. Fury asserts the inverse. The claim is a commercial engine, broadly machionable landing gear, and components drafted so hundreds of US suppliers can bid and build without exotic processes. That pushes work from a few certified bottlenecks to a distributed base. And the practical effect is simple. Shorter queues, predictable pricing, and interchangeable work centers when one shop is saturated. The engine choice illustrates it cleanly. Williams's FJ44-4M comes from a mass-produced business jet lineage with established maintenance, repair, and overhaul pipelines. There are trained technicians, standardized procedures, and stocked spares across existing service centers. By using that core, Fury sidesteps the scarcity that surrounds military-only engines, where parts flow through restricted depots and surge capacity depends on long-negotiated contracts. Anduril states the intent directly. Design for high-rate production using commercially available components and simplified manufacturing steps to cut bottlenecks. So the airframe's parts list favors operations most US job shops already run: CNC milling, turning, welding, and straightforward heat treatment, specified with tolerances that are tight enough for repeatable performance but not so fragile that only one vendor can hold them consistently over time. Think of the conventional fighter as a hand-built watch where jeweled movements demand a single artisan per sub-assembly. Fury behaves more like a modular, standardized tool. Precision stays where it matters. But the interfaces and process windows are documented for replication, so parallel lines can produce the same result without bespoke craftsmanship. By way of example, the landing gear is engineered so any competent machine shop can cut the legs and housings, and a regional welder can join them to spec. That reduces queue time because you are not trapped behind one certified forging run or a heat treat oven booked months out. In a demand spike, additional shops can be onboarded with drawings, inspection steps, and verification gauges rather than new metallurgy qualifications. Software-led iteration closes the loop. Semi-autonomous flight control allows faster integration cycles because autonomy handles routine envelope work while test teams focus on changes. Hardware can be reused between flights with updated software loads, which avoids the recertification drag common to bespoke programs where each minor hardware revision forces a documentation cascade and stand-downs. One way or another, the manufacturing strategy swaps specialization for breadth. You widen the supplier base, lower the sensitivity to any single delay, and convert schedule risk into workforce management. If you sum all of that up, timelines compress and unit cost trends downward because fixed overhead spreads across more airframes and rework falls as processes standardize. So, with the architecture mapped, we can move on to the specific part choices that either sustain this distributed model or break it under real production pressure, starting with the landing gear drawings and the engine support paths that determine whether surge capacity holds under stress. If a landing gear can be cut in Duluth and welded in Dallas, lead time in a crisis drops because work shifts from a single certified line to many competent shops that already run the required machines. and the queue no longer starts and ends at one bottleneck. The design intent is direct. Engineer high-demand parts so multiple shops can make them using CNC milling, turning, common weld processes, and straightforward heat treat. No exotic chemistries, no bespoke tooling that locks work to one vendor. Drawings specify interfaces and tolerances so sub-assemblies meet on the airframe without hand-fitting, and so a second or third shop can step in with minimal onboarding. Typical aerospace landing gear relies on specialized forgings with proprietary heat treatments and coatings backed by long qualification trails. That pipeline delivers superb fatigue life, but it couples schedule to a small set of furnaces and forge presses. Shift to broadly machinable designs, and you confront questions about durability, corrosion resistance, and qualification evidence under spectrum loading that includes hard landings, crosswind yaw loads, and catapult-grade vertical rates. The engineering trade is to anchor the structure in standard alloys, define tolerances where load paths demand it, and publish process controls that any audited job shop can follow. You specify grain direction requirements only where the stress map justifies it, and you call out surface finish, radii, and thread forms that reduce crack initiation. You then backstop quality with inspection steps, coordinate measuring of bores and lugs, die penetrant on weld toes, and you stabilize output with statistical process control so variation trends are caught early rather than after assembly. Anduril's stated approach is that any machine shop can build the gear, which implies explicit drawings, inspection regimes, and SPC as the quality spine. That package lets multiple shops run parts in parallel while holding interchangeability. It also allows swap out. If one shop's CPK drifts, another can pick up the run without requalifying the entire assembly, since the evidence resides in documented process windows and acceptance data rather than in a vendor-specific recipe. The engine decision follows the same logic. A commercial power plant, the Williams FJ44-4M, brings immediate access to spares, trained technicians, and predictable costs because it rides on an existing business jet support network. That means parts already sit on shelves at MRO centers and work cards already exist for routine tasks. So turn times are measured by shipping and labor, not contracting cycles. The trade is real. A commercial core respects civil durability and temperature limits, so extremes of the military envelope are constrained. But for a high-volume unmanned aircraft, the supportability gain outweighs the marginal edge case performance. Software-led testing compresses integration. Semi-autonomy flies the routine envelope, so engineers can inject updates quickly and observe effects in structured sorties, then roll back if behavior deviates. Hardware remains constant across cycles while software iterates, which avoids the recertification drag tied to physical changes. Lethal actions still require human approval, so autonomy manages navigation, formation, and sensor tasks, while weapon release sits behind an operator authorization gate. Risk control sits in architecture. A kill switch allows immediate mission abort and safing, and human-in-the-loop release ensures lethal authority remains with an operator even as production distributes across many shops. That division lets the industrial base widen without translating manufacturing scale into uncontrolled use of force. One way or another, landing gear buildable anywhere unlocks distributed surge capacity, reduces choke points, and stabilizes cost because a broad supplier base dampens single-point failures and price spikes. By this point, we have mapped the parts list to the shop floor and tied it to the engine and the software regimen. We can now close with what that means for schedules, for program budgets that survive audits, and for deterrence calculus when quantity and readiness start to matter as much as individual sortie performance. The real innovation here is industrial. The aircraft is drawn for the factories that actually exist, with processes most shops already run, and with documentation that lets parallel lines hold quality without bespoke rituals. It was therefore designed for throughput, not for unicorn vendors that never scale on time. Would you trust a forward scout that trades boutique parts for repeatable builds, knowing it can be fielded in numbers? And does deterrence now hinge on how fast you can build, not just how well you can fly? If you want a deep dive on how autonomy and human approval coexist in combat systems, say so in the comments, and we'll tackle that next.
Signal